Hi everyone. In this video, we will use what we've learned about the Lebesgue measure of sets to begin reconsidering the notion of integration that we previously saw in Math 5610. As we discussed before we began our section on the Lebesgue measure of a set, the notion of Lebesgue integration is to look at integrating from a different point of view. In this video, what we want to do is revisit that idea, see how what we have learned about Lebesgue measure of a set might be helpful here, and begin to think about what it might mean for a function to be measurable. So to begin, recall that the fundamental idea of the Riemann integral was to partition the domain into subinterval and approximate the area under that curve f with vertical rectangles. So we would partition our interval AB into a number of sort of small little widths, and then we would draw these rectangles, right, whose heights were the function values at some sample points chosen from that partition. However, Lebesgue's idea was to partition the range instead of partitioning the domain. So given some bounded function, we could partition the interval from f lower bar to f upper bar. So we would partition sort of the different y values that the function hits, and then draw rectangles that were more horizontally oriented than vertically oriented. Now, if we look at this sort of in a picture, right? So the idea here is I have my function f, and we could consider any function f, but in particular, I want us to consider a function that is not one-to-one, because that's where we really see the need for the Lebesgue measure. So imagine here, so if I were to come here for this function, I can see, here would be like my f lower bar. I could come up here, maybe sort of here's my maximum value. So this would be my f upper bar, right? And I go about partitioning my range, right? Now, imagine I do that, and here are two values in my partition, y sub k and y sub k plus 1. And if I think about here, what I'm doing is I'm going to choose the height of this subinterval to be the height of my rectangles. But now I want to sort of fill in this gap here, right? And what you see, right, is that I end up with these sort of disjoint pieces. Now, if you think back to something like doing a Riemann sum, right? You had to choose something like a left or a right-hand point rule, right? A left or right-hand rule. Here I have to choose almost an upper or a lower, and I'm sort of choosing an upper. Maybe this picture, maybe I'm not doing the greatest job, but I'm choosing, the upper function values here to help decide what the widths of these rectangles are. But again, notice here that because my function is not one-to-one, I end up with two disjoint sort of intervals making up the width of my rectangle. So if I think about what I want the contribution here to be, I can think about coming down here into the domain and looking at sort of this set. If I look at this set in the domain, these are essentially the x values that just map up to this upper line. Okay, so let me just for a second, let me call this set E. Okay, so E is the union of these two intervals. I would approximate these rectangles here by what? Well, their height would be something like a delta y sub k. Okay. Or actually, I guess this would be a delta y sub k plus 1. That'd be y sub k plus 1 minus y sub k times, well, I want the length of this interval would be the measure of this set E. Now, if I look at this set E, right, the first question I have to ask is, well, do I even know that E is measurable, right? It's just a set. Now, for this particular case, right, it appears that E is the union of two intervals. Intervals are always measurable. The union of measurable sets is measurable. So certainly this E would be measurable. But if I start to think a little more generally about what this E represents, this E really is what? It's the set of all x in my domain. Oh, all right, set of all x in my domain D, such that what? Well, it's really the set of all values such that f of x is greater than or equal to, in this case, y sub k plus 1. Right? It's all the x values, right, where I get out f of x being greater than or equal to y sub k. Right? Now, in general, I can ask myself, how do I know that this set is measurable? And the answer is, I don't necessarily know that. Without assuming anything else about f, I don't know that this set will be measurable. Now, if I make some additional assumptions about f, like f is continuous, right? F, even just assuming f is Riemann integrable, turns out, would be enough, right? But in general, I don't know whether this set is measurable so that this will even be defined. Okay? So before I can even begin to consider actually constructing the value of the Lebesgue integral, I have to deal with this notion of how do I know whether sets of this form for a given function will be measurable or not. And so that's the first thing that we are going to look at. We're going to think about what it might mean for a function to be measurable. Now, this shows us sort of if we want to carry that idea of Lebesgue integration a little further, right, we have to answer this other question first. So that's what we'll do. And so the first thing we're actually going to do, we're not going to define quite yet what it means for a function to be measurable, but we want to look at a theorem that tells us something about measurability of sets that are related to a given function. All right. So let f be an extended real valued function. So just this is a new sort of word. So this extended really here is going with real valued, right? So saying something is extended real valued, right, is really saying that f of x is either a real number, but I'm also happy for it to take on a value of plus or minus infinity. And now I'm going to consider that a legitimate output of a function, right? So when you think about a function like, say, f of x is equal to 1 over x squared, right? Typically, we have thought of that, say, as a function f, which maps from minus infinity to 0, union 0 to infinity into the reals, right? And we define the domain in this way because we say, oh, well, it's undefined at 0, right? Well, I could think of this as, I could think of taking this function and at 0, just defining it to be infinite. So I could say f of x is equal to 1 over x squared if x is not equal to 0, and it's equal to infinity if x is equal to 0. And one advantage of thinking about this function in this way is now, for example, you can actually think of this as a continuous function, right, over the extended real numbers, right? Because the limit as x approaches 0 of f of x is infinity. Okay. So this has some advantages. It has some drawbacks. It actually turns out that for Lebesgue measurability, or for Lebesgue integration, we actually just want to consider these functions as extended real valued functions. So we will allow them to take on the values of plus and minus infinity. All right. So let f be extended real valued. And let's assume further that f has a measurable domain D. So the domain that is defined on must be a measurable set. Now, it's a function that's defined on all of R is measurable, right? If it's a function that's defined on an interval, intervals are measurable. So often this is not, in practice, this is rarely an issue, but something to be aware of. We need the domain D to be measurable. If that is true, then the following statements are all equivalent. Now, if you look at each of these statements, they all look nearly identical, right? They each say for every R, the set, and then there's some set defined in terms of a function f, and the value r is measurable. So the first says for each for each r in R, the set of all x in the domain such that f of x is greater than r, or expressed another way, f inverse, the preimage of the interval r infinity, is measurable. Okay. So what is that saying? That's saying if you have some function, okay, so say here's f, okay, and let's say your domain D is the interval, say like the closed interval here. This is your domain D. If for every real number r, so imagine you come through here, you pick some real number r, the set of all x values such that f of x is greater than r. So here, let's see, what would that be? That would be like this interval. And then it would be here to the endpoint of the domain. Okay. So this set, this would be the set of all x in D such that f of x is greater than r. Okay. This is measurable, but then it has to work for every r. So as you move r, the question is each of these sets measurable? And again, what this theorem says is not that this is true, it says the following are equivalent. So if it is true that each of these sets is measurable for every r, then it must be the case that for each r, the set of all x in the domain such that f of x is greater than or equal to r is measurable. So basically, if I come through here in this case and just put closed brackets on each of these intervals. Okay. Number 3 says for each r, the set of all x in the domain such that f of x is less than r. Well, that here really is just the complement of this set in D. That would be like this. And so this yellow set here. And then the last one says for each r, the set of all x in the domain such that f of x is less than or equal to r. So you just change all these open endpoints to closed endpoints. It's measurable. Now, again, what this theorem says is if any one of these statements is true, then they all have to be true. If any one of these statements is false, then they must all be false. Okay. So what I want to spend most of our time doing in this video is I first want to see how we prove this theorem. It actually turns out that this is just a nice, straightforward application of some properties we know about measures of sets. Okay. But once we do that, I want to just work through some examples. Let's see how this applies to some particular functions. Okay. That will be essentially our goal for the rest of the video today. All right. So anytime I want to prove something that says the following are equivalent, the idea is I want to show that 1 implies 2. Then I want to show that 2 implies 3. Then I want to show that, a bit more room here. Then I want to show that 3 implies 4. And finally, I want to show that 4 implies 1. Okay. And now having done this, right, any one of them being true, like if I know then that 1 is true and I want to prove that 4 has to be true, well, if 1 is true, then 2 is true. If 2 is true, then 3 is true. And then if 3 is true, then 4 is true. So then 1 implies 4, right? And you can work these out in any order then. All right. So the first thing I want to do, right? So if I want to show that 1 implies 2, let's see, what is the thing I want to prove then? Well, then I want to show that this set, oh, sorry, this set, I want to show that this is measurable for every R. Okay. Well, so that's what I need to show that 2 holds, but I get to assume that 1 is true. Okay. Well, note that I can write this as the intersection n equals 1 to infinity of the set of all x in D such that f of x is greater than r minus 1 over n. So let's just think about why this is true. If you want to prove a set equality, right, you show that the left-hand set is a subset of the right-hand set, and the right-hand set is a subset of the left-hand set. So let's take an x in here in the left-hand set. Then that means that f of x must be greater than or equal to r. Well, if f of x is greater than or equal to r, then certainly if f of x is greater than or equal to r, then it's certainly strictly greater than r minus something. Okay, so for every n. So if x is in the set of all x such that f of x is greater than or equal to r, then it's in every one of these sets, so it's in the intersection. Okay, so the left-hand set is a subset of the right-hand set. Now, let's try to work the other way. Okay, take something in this intersection. Okay, that means if it's in the intersection, that means that f of x must be greater than or must be strictly greater than r minus 1 over n for every natural number n. So I can take a limit then as n goes to infinity, and I get that f of x must be greater than or equal to r, because 1 over n goes to 0, and so it must also be in this set. Okay. So you get that these two sets are equal. Now, why is this helpful? Well, we're assuming 1 is true. 1 says that sets of the form all x in the domain such that f of x is greater than some number, no matter what number this is, they're always measurable. So each of these sets is measurable. So I have a countable intersection of measurable sets. Countable intersections of measurable sets are measurable. And so this set must also be measurable. All right, great, perfect. All right, so we have 1 implies 2. Okay. Now we can make a very similar argument for 3 implies 4. So I'm going to jump to 3 implies 4 because the idea is essentially the same. So for 4, you want to show that the set of all x in D such that f of x is less than or equal to r. You want to show that's measurable, but you can write that as an intersection n equals 1 to infinity of set of all x in D such that f of x is less than r plus 1 over n. Now, again, you can prove this set equality in an almost identical way to the way we did it here. Okay. Then you have from 3 that sets of this form, sets of the form, the set of all x in D such that f of x is less than some real number, they are all measurable. So all of these sets are measurable. So I have a countable intersection of measurable sets. That must be measurable. So this set is measurable. All right, perfect. Now, 2 implies 3 and 4 implies 1, I actually think are a bit simpler. And I think they're a bit simpler because you can actually just use sort of a trick here. So if I want to show that 2 implies 3, right, then I want to show that the set of all x in D such that f of x is less than r. That's the part from number 3. I want to show this is measurable. But if I think about it, this is really the set of all x that are in D such that f of x is greater than or equal to r complement, right? But now I have to do something a little careful here. I have to intersect it with D. So if I take the complement of this set, so this is the set of all x in D such that f of x is greater than or equal to r, by 2, this is measurable. Okay. Now, this is measurable, so its complement is also measurable. But its complement is not exactly this set because the complement of this set also includes things that are not in the domain. In fact, it includes every x that's not in the domain. So we have to intersect it again with the domain to get us back to this set. So the complement of this set gives us everything that's not in the domain plus things that are in the domain, but for which f of x is strictly less than r. So we intersect it with the domain to get back just the x values that are in the domain such that f of x is strictly less than r. Okay. In any event, our assumption by 2 is that this is measurable for every value of r. The complement of a measurable set is measurable. The hypothesis of the whole theorem was that the domain D is measurable, and the intersection of measurable sets is measurable. So this is measurable. Now, we play an again, nearly identical game here. If I want to look at, so for one, I want to look at the set of all x in D such that f of x is greater than r. We can write that as the set of all x in D such that f of x is less than or equal to r, complement, intersect D. Again, this from 4 is what we're assuming is measurable. The complement of a measurable set is measurable. D is measurable, and the intersection of measurable sets is measurable. So this ends up being measurable. Okay. So this completes the whole proof. All right, we have shown that if any one of these conditions is satisfied, then all of them must be satisfied. Okay. Now, collectively, we will refer to these 4 different conditions. We could refer to them all separately, but again, they're all equivalent. So in some ways, giving them all different names wouldn't be particularly helpful because as soon as one of them is true, they're all true. So we just sort of collectively refer to these as the measurability conditions, and we don't really bother with distinguishing one from the other because again, as soon as any one of them is established, they all have to be true. All right, so if I have an extended real value function f that has a measurable domain, and if it satisfies any one of the measurability conditions, which of course means that as soon as it satisfies any one of them, it satisfies all of them, then I say that f is a Lebesgue measurable function, or sometimes, and particularly in this course where we're only going to be discussing Lebesgue measure, we just simply call it a measurable function. Okay. Now, I do want to note there is a quick corollary that if f satisfies any of the measurability conditions, then for each real number, the set of all x such that f of x is equal to r must also be measurable. However, it is not equivalent to the others because it is possible for a function to satisfy this condition but not satisfy the others. So in particular, this is true because this set of all x in the domain such that f of x is equal to r, right? You can think of this as the the intersection of the set of all x in D such that f of x is greater than or equal to r, intersected with the set of all x in D such that f of x is less than or equal to r. Okay. So if the measurability conditions hold, then each of these is measurable. Therefore, their intersection is measurable, and their intersection is just this. Okay. However, it's not possible to go the other way. It's not possible to say that if this is measurable, each of these is measurable. And in fact, you can construct counterexamples to this. So this is something we may make use of, and it's worth noting. But mostly it's worth noting to note that it's not equivalent to the measurability conditions. It follows from the measurability conditions. All right. So Let's then look at some examples. Okay, we understand sort of, what this definition is, but let's try to prove that like the function f of x is equal to x is measurable. So if I want to prove a function is measurable, I really need two things. The first thing I need to look at is what's the domain. Okay. Now, in this case, right, I guess I could specify it, right? I could say I'm looking at this function on the interval AB. And if I was doing that, then the domain would just be AB, and that's an interval, and so it's measurable. Here, since I haven't specified a domain, I'm just going to think about the natural domain. Here, the domain of this function is all real numbers. This is measurable, right? All of R is always measurable. The empty set is always measurable, right? So that's measurable. Great. Now, the second thing I need to do is I need to show that the measurability conditions are satisfied. I can do that by proving that any one of the measurability conditions is satisfied. Let's just use the first one we had written down. So let's look at the set of all x in the domain such that f of x is greater than r. Well, what do I know? I know that this is the set of all x, and I know what my domain is. My domain is all reals. This is a set of all x in R such that f of x here is just the function x, such that x is greater than r. And I could ask myself, well, how do I know that's measurable? Well, this is just what? This is just the interval from r to infinity. Okay. In particular, it's an interval, and all intervals are measurable. So this is measurable for every r since it is an interval. And we proved that all intervals are Lebesgue measurable, and their Lebesgue measure is just their length. So the Lebesgue measure of this is infinite, but it is still Lebesgue measurable. So the function f of x is equal to x is measurable. Okay. And in fact, if you wanted to take and restrict this, you might wonder, if I take this function and then restrict its domain to a measurable set, will that still be measurable? And the answer is yes, because if you changed your domain to say some measurable set E, okay, then this would just be intersected with E, right? So this would be the set of all x in E, such that x is greater than r. This would be an interval which is measurable, intersected with a measurable set E. This is measurable for each r because it's an interval. This is measurable by assumption, and the intersection of measurable sets is measurable. Okay, so not only does this work on all of R, it also works on any measurable set. Okay, so if you wanted to restrict your f to an interval, that's fine. If you wanted to restrict your function f to the rationals, right, that would still be perfectly fine, right? As long as you have a measurable domain, the function f of x is equal to x will be measurable. And again, I mean, you sort of hope that's the case, right? We'd really be in a weird spot if the identity function was not measurable, right? We would have to ask a lot of questions about whether we were really looking at something that was going to be mathematically valuable if it doesn't apply to like the most standard example of a function. All right, let's look at a slightly different function. Let's take g of x is equal to x squared. Okay. So if I take g of x is equal to x squared, I want to do the same thing. So let's first think about its domain. Again, the natural domain here is all of R. Okay, we can come back later and say, okay, what if it wasn't all of R? Okay. And that's measurable, so we're good there. Okay. And now again, we need to look at, are any of the measurability conditions satisfied? Right? As soon as one's satisfied, they're all satisfied. Now, maybe here, let's choose something different just to use a different one of the measurability conditions. Let's say I'm going to look at the set of all x in my domain such that my function g of x is, let's say, less than or equal to r. Now, again, I can my domain is all of R. So set of all x in R such that g of x, that's x squared, is less than or equal to R. All right. So before, when we had just the identity function, we were able to re-express this as just an interval. I want you to pause the video and see if you can think about what these sets might look like. And in particular, do the form of these sets change as your R value changes? Remember, eventually we want to prove that this holds for all values of R. So these sets might look different for different values of R. So pause the video, take a moment, and see if you can make sense of what these sets might look like in some or all cases. Okay, let's take a look. Now, it turns out here I'm going to need to break this into really three cases. I'm going to need to break this into a case where R is greater than 0, where R is equal to 0, and where R is less than 0. So if I just think about just this inequality, x squared is less than or equal to R, right? If I take R to be some negative number, right, that really means I want to know for what values of x does x squared give me a negative number. There are no x values, no real x values that do that. I'm looking over the reals. So here, this would actually be the empty set if R is less than 0. Okay. If R is equal to 0, okay, so then I would be looking at where is x squared less than or equal to 0? Well, x squared is never less than 0, but it can be equal to 0, but that only happens when x is equal to 0. So when R is equal to 0, I get back the single point 0. Now, when R is positive, okay, when R is greater than 0, I do in fact get solutions here. And here, my solutions would look like negative square root of R is less than or equal to x is less than or equal to square root of R, or written a different way, here I'm looking at the closed interval from minus square root of R to positive square root of R. Okay. So notice here that the form this set takes does depend on my value of R, right? However, regardless of which case I'm in, this is an interval when R is greater than 0. This is an interval. Intervals are measurable. Here, R is equal to 0. This is actually a finite point set, right? It's by the same argument that countable sets have Lebesgue measurable and have Lebesgue measure 0. This also single finite point sets have Lebesgue measure 0. And finally, right, when R is less than 0, this is the empty set, which again is also measurable. Okay, so regardless of the value of R, I always get that this is a measurable set. So this is measurable for all real values R. Okay, and hence this function x squared is measurable. Now, we could continue, we could try x cubed and x to the fourth and so on and so on and so on. As you might imagine, it could get a little messier to deal with. And then when we start trying to add them together, say to prove that polynomials are measurable, you have to solve these polynomial inequalities, which, I mean, maybe we can do in theory, but in practice, it's just really quite messy. And think about generally how we do things like this. When we define something for a function, like say continuity, right? We probably proved that f of x is equal to x was continuous at any point in its domain. But then what we did is we actually showed that products of continuous functions were continuous, and that sums of continuous functions were continuous. And that allowed us, for example, to take just the fact that f of x equals x was continuous, and from that show that all polynomials had to be continuous. In a similar way, we don't want to try and show something like all polynomials are measurable by trying to go through case by case. First of all, countably infinitely many of them, so we don't want to do that. But secondly, what we'd like to do is maybe prove that the sum of two measurable functions is measurable, and the product of two measurable functions is measurable. We'd like to explore that theory first, before we sort of try and go off and do lots and lots of cases. Okay. So this has been a good exercise to just sort of see how that definition works, but it's not really the avenue we want to pursue to show, for example, that all polynomials are measurable. Now, the last thing I want to do in this video is I actually want to introduce two new kinds of functions, or you might have seen, we're going to first talk about step functions. You've probably seen these before, but we'll sort of think about them in a slightly different way. So I want to define a step function, and so that I'll say that a function phi from a closed interval ab into R is a step function if there is a partition of the interval AB such that phi is constant on each open subinterval of the partition. In that case, we can then write the function phi as a sum, k equals 1 up to n, of ak times chi of I sub k, where a sub k is just the value, the constant value that phi takes on the interval ik, and ik is just defined to be this open interval. Now, there are a lot of moving parts here, so let's try to make sense of this. So, again, you probably remember step functions. So let's say you have an interval AB, and let's just draw something that we would roughly think of as a step function here. And it doesn't have to be, there's no rule that it has to be strictly increasing or anything like that. Okay, so here's an example of something we might call a step function. Okay, now, under this definition, why is it a step function? Well, I can take a partition of AB. So if I take a partition, x0 is always the left endpoint. And then I'm just going to order the breakpoints of my step function, right? That's all I'm doing here. And then my last one is the right endpoint. Okay, so there's my partition of AB. Now, this subinterval would be I1, would be I2, this is I3, this is I4, right? And notice that on the open subinterval, so forget about the endpoints, but on the open subinterval, this function is constant, right? On I1, this function is constant. On I2, this function is constant. We don't include the endpoints because if we included the endpoints of I1 here, this function would not be constant. It takes on it jumps at the right endpoint, okay? So we don't care about the endpoints. We really just care about what happens on the open interval, okay? So this is a step function. Okay, great. Now, what is this telling me? This is really telling me that another way I could write a step function is you should look at this as, in this case, this would be a sum of 4 functions. The first function, so I can think about decomposing this. I'm going to sort of try to line this up a bit. So sort of just map these things up. Here's A, here's B. So the first function is going to be A1 times chi of I sub 1. Now this chi of I sub 1, that's the indicator function. So in general, the indicator function of a set A is 1 if x is in A, or 0 if x is not in A. Okay. So if I'm on the k is equal to 1 case, I have A sub 1. Okay, what is A sub 1? A sub 1 is phi of I sub 1. It's just the constant value that this interval maps to. Okay, so I come here, and when x is in I1, okay, what's going to happen? When x is in I1, chi of I1 will be 1 times A1. So what I'll get here is just this back. Now, as soon as I'm outside of I1, my indicator function will be 0. And so everywhere else, this function will be 0. So what the first term in this sum is just this step and then 0 everywhere else. The second term in this sum is going to be A2. Well, A2 is just the constant height here. It's the constant height on the second interval times chi of I2. So really all it's going to do is it's going to give you back the second step here, but everywhere else it's going to be 0. Okay. And you continue on, and essentially what this is doing is it's decomposing your step function into a sum of functions, each of which just gives you one of the steps and is 0 everywhere else. Okay. Now, I think this is a little weird the first time you see it to think about like why is this actually true, right? Does this actually give me back the same thing? But then secondly, once you realize that the answer is sort of like where the question becomes why, right? Why is it helpful to write it like this? Well, we'll actually see in a bit that this is, well, not in this video, but in subsequent videos, that this is actually a really helpful way to think about these step functions because they're just, it turns out to be a nice way to define the Lebesgue integral. Okay, so this allows you to decompose a step function. Essentially, this step function has 4 steps. You can decompose it into a sum of 4 functions, each of which is just one single step. Okay. And in general, if you have n different steps, right, then you can decompose this into a sum of n functions, each of which has 1 step. All right. Now, step functions. They're nice functions. They're certainly Riemann integrable. Okay, so we might hope that they're Lebesgue integrable. Okay. We could ask ourselves, are these functions measurable? Okay. And the answer is yes. Let's think about why these functions are measurable. Well, suppose I finish erasing this. So suppose I have this step function phi, and let's say I want to look at the set of all x in my domain, which is AB, such that phi of x is greater than R. Now, what for some real number? Now, really, what happens? I only have finitely many steps in my step function. So I really just need to select out which of those steps are greater than R. Okay. So I look at all the AKs and I say, well, which of these are bigger than R and which of them aren't? Okay. For the ones that are bigger than R, then I need to include those I sub k's in a union, right? So visually, I have these steps, right? You know, whatever's happening. I come and cut with some R. Okay. I need to identify the steps here, or the intervals that go with the steps that are above this cutoff R. Okay. So it turns out you can express this set as a union over, so you basically figure out which of the AKs is greater than R. And for those Ks, you union together their corresponding I sub Ks. Okay. But each of these I sub Ks is an interval. This is a finite union of intervals, which is measurable. Therefore, this set is measurable. Therefore, the measurability conditions are satisfied and step functions are measurable. All right. Now, as soon as you do this, okay, you start to realize that you could probably generalize this a little bit. And it didn't matter so much that here for the measurability that we had intervals. It just mattered that what we had here was a measurable set. So what if instead of defining, here I defined a step function, it needed to be constant on these intervals. What if I replaced interval here just by measurable set, right? If I replace interval by measurable set, then everything basically works out the same because here I just get, let's say those are EKs, right? But I still get a finite union of measurable sets, which is measurable. Okay. Well, that's exactly what we're going to do. We're going to generalize the notion of a step function to something called a simple function. Now, The relationship between step functions and simple functions is like that between squares and rectangles, right? So every step function is a simple function, but not every simple function is a step function. So a simple function, so instead of phi, now we're going to use psi. A function psi is a simple function if the range is a finite set, and for each k, the preimage, so that's psi inverse of ak, is a measurable set. So that is, we can write psi of x as a sum k equals 1 up to n of a sub k times the indicator function of this set ek. Okay, so again, it's exactly the same idea. You have finitely many outputs. I could take 4 of them here, let's say. Okay, but now instead of saying, well, you can only attain the value a1 on an interval, I can allow myself to take the value a1 on any measurable set. So it could take a1 on this is a measurable set. This is 2 intervals and a single point. Over here, it could take the value a2 at some, maybe this is some weird infinite set, and this is some interval. But again, altogether, they're measurable. Okay, the set of all x values where your output value is a2 is measurable. And again, you can continue doing this. So this could take some of the other values here, right? And then, maybe that's all that happens at a3, and then maybe at a4, right? I don't know what happens at a4. Maybe we just get a single interval here. I guess I need to make that open. All right. So it's sort of like a step function, but your steps don't have to be these nice intervals anymore, right? You can instead have these weird sets as long as the sets themselves are measurable. Okay, so all we're doing is generalizing here the notion of a step function to allow the steps, the pre-images of these particular output values, they don't have to just be intervals anymore. They can now be any measurable set. Okay. Now, why are we talking about all this? Well, it turns out, step functions and simple functions, again, they're examples of Lebesgue measurable functions. But also, if you start to think about like what the integral of this function should be, so if I take a step function, so let's imagine I take a step function, okay, it's pretty easy. The step functions are actually Riemann integrable, right? And so what I get back for the integral of a step function, right, is I take its height times the length of those intervals, right? And that's just the Riemann integral, right? That's the value of the Riemann integral. What I'd like to do is generalize this for step functions. Now for simple functions. Now I have a problem here though. These functions need not be Riemann integrable. Okay, so I can't actually, like the indicator function of the rationals, okay, this is not Riemann integrable, okay, and even on like say 0, 1, so this intersect 0, 1, this is not Riemann integrable, okay, but right, I can express this. This is just 1 if x is in Q intersect 0, 1, which by the way is a measurable set. It's 0 otherwise, right? And that complement has to also be a measurable set. So this is, in fact, a simple function. I feel like I should be able to integrate this by just saying, well, I take the height of the function times, well, okay, I can't take the length of these intervals anymore, but I should be able to take the measure of them. That's the whole reason, right? We wanted this, right? To replace lengths of things by measures. So what we will do moving forward is we will actually first define the Lebesgue integral of a simple function in precisely this way, and then see how we can use that to define a Lebesgue integral for non-simple functions. So I would encourage you to spend a little time trying to internalize and make sense of these step functions and simple functions, exactly what's going on here, because they will be incredibly important, particularly simple functions, in defining the Lebesgue integral moving forward.